afternoon, we were discussing the properties of the cosmic microwave background radiation, and in the last lecture we had worked out that the number density of particles for any particle distribution, not only cosmic microwave background radiation, this is for any particle density. So, we were dealing with photons. So, for photons the number density of particles with is written as, can be written like this. I had told you this in the last class. So, this is the number density of particles with angular frequency in the range omega and omega plus d omega, and having direction in the solid angle d capital omega. So, these are particles which are moving in this solid angle with this angular frequency. N omega is the occupation number written as a function of the angular frequency. In principle, it should be written as a function of the mode or the wave vector or the momentum, but you can also equivalently write it in terms of the angular frequency using the dispersion relation. Okay. So, this gives us the number density of particles with these properties. Now, we had used this to calculate the energy density of a thermal distribution of photons, and we shall come back to this shortly. But before coming back to this, let us now take up another interesting quantity, the specific intensity. Okay. I have defined, so let us just look at how the specific intensity of light is related to this occupation number of the mode. Okay. So, how was the specific intensity defined? The specific intensity this was defined as follows. We had a unit area or area dA, and the solid angle d omega. So, the energy coming in through this solid angle into this area dA is dE, and this is equal to I nu dA d omega, and this is the energy coming in a time interval dt in the frequency interval d nu. Right, that is how the specific intensity is defined. Now, the question is, how is this related to the particle energy density that we have just considered? Okay. So, suppose the region of space over here has particle energy density d nu. So, dE, how is this related to the photon energy density in this region? That is the question. Okay. So, this we can write this as dN, the energy density of photons in this region. Now, this is the energy density, so per unit volume. This is the energy in the frequency interval d omega, all these. So, these two factors are already taken care of. The question is, in a unit time, how much energy will cross this area dA. Since the photons are moving at a speed c, we can say straight away that this is going to be h cross omega into dA c dt. So, all the photons in this volume are going to cross through, that is the energy that will pass through in a time dt in the area dA, and this is the number density of photons. So, I have to multiply it with the energy of each photon. Okay, so we can write this also as then 2 n omega, the occupation number, into let us switch over from this angular frequency to the frequency, because we want to compare it with this expression. So, if I switch over to the frequency, then this is equal to h cross, this is 2 pi nu. So, there will be factor of 2 pi coming from here, another factor of 2 pi. So, there will be a factor of 2 pi cube which will cancel out with this 2 pi cube over here, right. So, we can write this as n omega h nu, and then I will have a factor of nu square. So, this becomes nu cube d nu by d omega c dt dA by the 2 pi's have all gone. So, I have a factor of 1 by c cube over here. So, this becomes this c, and there is a c over here, this cancels out. So, we can now identify what the relation between the specific intensity and the photon occupation number of that mode, corresponding mode. So, we see that the specific intensity I nu is equal to 2 times the photon occupation number, 2 photon occupation number h nu cube by c square, right. The rest of the factors are all same. So, this is h nu cube by c square. Okay, so that is the relation between the photon occupation number n, which we have written as a function of omega. It could have equally well been written as a function of the photon momentum p, the momentum of the mode, and the specific intensity. So, if I know how many, what is the occupation of a mode, so there is a correspondence between this specific intensity and the occupation number. That is the crucial point. Now, there is something very interesting. There are very interesting consequences of this. So, let me tell you what these very interesting consequences of these things of this relation is. This is a very interesting, very useful relation. Okay. So, the main interesting consequence of this is, consider a situation where the frequency of the photon has changed. Okay, this is what happens when radiation gets redshifted. So, by whatever means, for example, due to the expansion of the universe, if the frequency of the photon gets changed, that is what we have been discussing, right. But the photons do not get destroyed. That is the situation that happens when the universe expands, right. The occupation number is not changed, the photon just, its frequency just gets changed, right. So, in that situation, this occupation number is just the same, just that it now corresponds to a different frequency. Okay. Now, you can see that the I nu by nu cube is 2 n, I can write it as nu also if you wish, omega and nu are equivalent, by c square, and if the frequency of a photon changes due to some reason, they say during the propagation, there is a source here and the source emits light with a certain specific intensity, it is received here, this is emitted at a frequency, let us say nu, it is observed at a frequency nu prime, that is what happens due to the expansion. Question is, what is the relation between the specific intensity of the light emitted and the light observed. Okay. Now, we have seen that in the expansion of the universe, that is, the occupation number does not change. So, what we can say is that I nu, the specific intensity, by nu cube is a conserved quantity, right. This is a conserved quantity. So, in such a situation, I nu prime by nu prime cube is going to be equal to I nu by nu cube, and from here straight away you can say what the specific observed specific intensity is going to be. Okay. So, this is true for anything that does not destroy the photons, okay, where the occupation number remains unchanged. Okay. Actually, it is even more profound if you have something that is a canonical transformation, I mean where the phase space volume is preserved, then this kind of a thing goes through. Okay. So, let me give you a problem related to this, a very interesting and useful problem. The CMBR I have told you is like a black body, it is a black body radiation inside which we are immersed. So, there is an observer immersed in the CMBR. Okay. Now, this observer, there is a frame of reference in which the CMBR is isotropic. Okay. Now, this observer O is actually moving with a speed v, which is much smaller than c, with respect to the frame where the CMBR is isotropic. Okay. So, the question is what kind of a radiation does this observer see? The observer at rest with respect to the CMBR sees a black body radiation, I shall just come to that, sees a thermal radiation at a temperature T. Okay. The question is, there is an observer moving at a speed v with respect to that frame. So, what kind of radiation will such an observer see? Okay. And you can work this out by just using this relation, because you know that the radiation is going to get Doppler shifted. The Doppler shift is going to be different in different directions. It is going to be blue shifted in this direction, red shifted in this direction. Same photon is going to appear blue to this observer, appear at a higher frequency to this observer if it comes like this. It will appear at a lower frequency if it comes like this. It will appear at the same frequency if it comes like this. Okay. So, the same thing is going to appear at different frequencies to this observer, and you can use this relation to find out what this observer is going to see. Okay. There is another observer OR, let us say, who sees a thermal radiation at a temperature T, isotropic thermal radiation at a temperature T. Okay. This is at rest with respect to the CMBR. There is another observer moving with V much smaller than C. Now, the next thing is that what is the specific intensity corresponding to thermal radiation. Okay. What is the specific intensity corresponding to black body radiation, thermal radiation? Okay. So, inside this black body cavity at a temperature T, what is the specific intensity? It is same in all directions. Okay. So, to determine that, what one has to do is you have to just put in the occupation number of black body of thermal, the Bose-Einstein distribution, right, and what you get is that for thermal radiation, the black body radiation I knew, this is just a function of the temperature, and it is often denoted by B nu T, the black body radiation. This is 2, then we have h nu cube by c square, and here I have exponential h nu by k T minus 1, right. That is the Planck radiation formula, the Planck spectrum, right. That is the specific intensity that is observed inside the black body cavity, right. We have worked this out from first principle, assuming the Bose-Einstein distribution. Okay. So, the question that I had asked you just now is that there is an observer inside the CMBR who sees that kind of a spectrum. Now, another observer is moving with the velocity v with respect to this observer. What will such an observer see? Okay. Now, often it is of interest to study a situation where h nu is much smaller than kBt. This is the Boltzmann constant kb. Okay. The frequency is much smaller than this. So, in that limit we can expand this exponential as 1 plus h nu by kT. So, then I have minus 1. So, this will approximately be equal to 2, the 1 that comes from this, the first term will cancel out with this, the next term is h nu by kT, h nu will cancel out. So, I am going to be left with kT will go on top, right, h nu will cancel out. So, I am left with 2 nu square by c square kb t, which is also equal to 2 kb t by lambda square, the wavelength. Okay, energy per area, that is the dimension of specific intensity. This is called the Rayleigh-Jeans limit. Okay, this is the Rayleigh-Jeans part of the spectrum, the large wavelength part. H nu being small means that the wavelength is very large. Okay, Rayleigh-Jeans limit. So, this is the low frequency part of the spectrum. Okay, it is in the low frequency part of the spectrum, it is proportional to nu square. It is a parabola, it just goes up parabolically and then it reaches a maxima and falls. Okay, so, this part of the spectrum where nu is small, it is the black body radiation is well approximated by this. Okay, this is the Rayleigh-Jeans part of the spectrum, and this is very commonly used in radio astronomy, because radio astronomy deals with large wavelengths. Okay, typically the wavelength, this relation is satisfied in radio astronomy, much of radiation dealt with in radio astronomy. So, this is very useful in radio astronomy. Okay, this is a Rayleigh-Jeans limit. So, now let us move on. I have told you how the specific intensity is related to the occupation number, and I have also given you a problem to calculate the effect of motion of the observer on the CMBR. Okay. And this exercise is not just a hypothetical exercise, because it turns out that V, an observer located at our position, is actually moving with respect to the CMBR. So, this is something I shall wait till you work out the problem and then I shall discuss this. Okay. Now, so let us just recapitulate what we have calculated. We have calculated the energy density in the thermal radiation, and we have worked out the relation, the specific intensity corresponding to the thermal radiation, how it is related to the occupation number. We have also worked out some properties of the specific intensity. Okay. So, now let us take up a question. The question is as follows. The picture, let me just remind you of the picture. I am an observer over here. I see the CMBR around me. If I go back into the past, the CMBR is coming from this, light propagates at the speed of, at a constant speed c. So, the CMBR that I am seeing is coming like this. If I go back into the past, the temperature of the CMBR was much higher, right. Actually, if it evolves freely, the Planck spectrum, the thermal spectrum is unchanged, the spectrum that we have worked out is unchanged. All that happens is that the temperature increases. Temperature, so as I go back into the past, the temperature increases inversely with the scale factor, or it increases proportional to 1 plus the redshift, right. So, as I go to higher and higher redshifts, the temperature, the distribution, the form of the distribution remains the same, because it is moving freely, we have worked it out. The temperature just scales like this. Now, this radiation does not interact with matter. Now, if you go sufficiently back into the past, at a certain epoch, it is known that this is at a redshift of around 1000, the temperature is sufficiently high and this radiation interacts with the matter. Okay, it ionizes the matter and they are now in thermal equilibrium. They are interacting, not in, they are interacting and are in thermal equilibrium. Okay. Now, the question is this: suppose we are seeing a radiation which is non-interacting now. Now, somewhere in the past, and it has a thermal shape spectrum, sometime in the past it interacts with matter. So, the question that we would like to now see is that in this interaction, it will lose some energy or it may gain some energy from this matter, right. If the matter is cooler, then it will lose energy to this matter, it would have been losing energy or it. So, this interaction actually we are just following the evolution backwards in time. So, in this picture it is free all the way up to here, here it interacts with matter, okay. The matter is dense and the radiation is hot, so it interacts. The question is, what is the effect of this interaction on the radiation? Okay. So, to estimate this, let us work out the heat capacity of the radiation. Okay. So, the internal energy of the radiation U gamma we have worked out is this Stefan-Boltzmann constant T to the power 4. So, presently this is a, if you want to calculate this at present, put in the present temperature, right, and this, okay. So, this is the energy density. To calculate the specific heat capacity, you have to differentiate this with respect to temperature. So, this is the heat capacity at a constant volume, let us say, is 4 the Boltzmann constant T cube, okay. That is the heat capacity of the CMBR. Now, let us work out the heat capacity of the baryons, of the matter with which it is going to interact over here. Now, the internal energy, think of the matter as monoatomic gas, okay. So, the internal energy of this we know is 3 by 2 into the number density n of baryons, and baryon, right, baryons we mean protons and neutrons, right. So, think of it as just protons basically, hydrogen atoms, okay. So, the universe is made up of hydrogen mainly, let us say. So, let us just do an estimate, assuming it is made up of hydrogen, the whole universe is made up. So, the baryons in the universe are just protons, let us say, and there are electrons also. So, it is hydrogen atom. It is neutral all the way up to here where it becomes ionized. Once it is ionized, the matter radiation interacts with it. So, the energy density is for a monoatomic gas is 3 by 2 Nb, the number density, Boltzmann constant into temperature, okay. This is the number density of baryons. So, the specific heat capacity of this is 3 by 2 Nb, number of density of baryons, into the Boltzmann constant Kb. Okay. So, we want to calculate the ratio of these two numbers, okay. So, we would like to estimate the ratio of the heat capacity in the baryons to the heat capacity in the of the CMBR, okay. So, let us estimate this ratio. So, it is straightforward to calculate. We know the Stefan-Boltzmann constant. All that you have to do is you have to calculate the number density of baryons. The number density of baryons is very simple to calculate. Let me do it here. Number density of baryons. How will you calculate this? So, we know that the critical density of the universe is rho critical naught, right. That is the critical density of the universe. Now, the density parameter in the baryon, okay. So, let us say that the density parameter in the baryon is omega baryon, okay. That is the density parameter in the baryon at present, okay. So, this will give me the density of the baryons, and what I have to do is I have to divide this by the mass of one proton or one neutron, which is approximately the same, and I will get the number of hydrogen atoms, or mass of one hydrogen atom, okay. Mass of one hydrogen atom, if I divide it, then I will get the number of particles, number of gas particles, okay. So, I put in this number over here and I then determine this ratio. So, this ratio turns out to be, so the ratio of the heat capacity of the baryons to the photons, this ratio, okay. So, this ratio is this ratio of the heat capacity of the gas, of the matter, of the baryons by capacity of radiation, it turns out to be equal to, approximately equal to 4 into 10 to the power minus 9 omega baryon h square. Okay, this h square is the Hubble parameter, h in the Hubble parameter. That comes because this rho critical naught has 3 h naught square. Okay, so it depends on the value of the Hubble parameter. So finally, the ratio of the two specific heat capacities is 4 into 10 to the power minus 9 omega baryon h square. Okay, and this number omega baryon is something of order unity or less, not more than 1, definitely. Okay, so what we see is that the heat capacity of the matter, of the baryons, the baryonic matter, dark energy does not interact with radiation. Okay, so at most the whole critical density is in the baryons. So at most, but it is not so, right. So this number, the ratio of the heat capacities is an extremely small number. So what we learn from this is that when the radiation comes to equilibrium with the matter, the radiation is not affected, it loses a very small fraction of its heat, 10 to the power minus 9, okay, and or less depending on omega baryon h square. So the radiation is not affected. So the thermal radiation that we see now would have continued to be the same thermal radiation even after it is in equilibrium, even when it was in equilibrium with the matter. The process of interaction with the matter, the exchange of heat is extremely small, exchange of energy. Okay, so that is not affected. So we can just think of it as just in moving, as if it were moving freely, right. The effect of the interaction is extremely small on the radiation. So you can go back, even when it interacts, you can just take the same temperature and scale it as 1 plus z, even beyond that, higher redshifts than that, okay, because it does not lose much of the energy. Let me just give you the number. Omega baryon observations indicate that omega baryon h square is 0.02. Okay, so it is extremely small. 4% of the universe I had told you was in the baryons, right. So it is an extremely small number, it is a small number. So this ratio is very small, right. Now next thing that we shall look at, so we have worked out the energy density. The next thing that we shall look at is the number density of CMBR photons. Okay. So how do we calculate the number density? I have this expression for the number density of particles with angular frequency d omega moving in the solid angle capital D omega. Now if I want to calculate the total number density of photon, I am not interested in this omega, the angular frequency information, neither am I interested in the solid angle information. So I have to integrate over all of these. Okay. So the number density n is what I get when I integrate over all of these, right. Now if I integrate over all solid angles, I get a factor of 4 pi. So in the numerator I will have 8 pi, the solid angle integration will give me 4 pi, right. I am interested in photons moving in all directions, I just want the total number density of photons. Okay, this gives me the number density of photons with in this direction, in this solid angle, moving in this solid angle with this angular frequency. Okay, so total thing I have to integrate. So I have 8 pi, I have 8 pi cube here. So I have, this gives me a factor of 1 by pi square, and I have a factor of c cube over here. Then I have the occupation number which I have to put in. So I have to put in the occupation number. The occupation number we know is exponential h cross omega by kb. I am dropping the subscript b for the time being, kbt minus 1, and I have to integrate over all omega. So I have omega square d omega. I have to do this integral from 0 to infinity, right. That is the number density of particles. So this is it. I have to just integrate over omega. Now what we do is, again same thing, you substitute y is h cross omega by kT, where this is the Boltzmann constant. Okay. So, with this substitution, this becomes y square dy integral 0 to infinity e to the power y minus 1. Now, let us write the factors outside. The factors outside are going to be k t by h cross omega, no, k t by h cross cube, right, because there is one factor, two factors are going to come from this, one from this. So, this is going to be equal to 1 by pi k t by h cross c 1 by pi square, sorry, this is pi square cube. Okay, that is the number density of photons and this integral is a constant number. Okay. This integral is a constant number. So, let me put this here, this integral 0 to y square dy by e to the power y minus 1 is a constant number. This is the Riemann zeta function. This is twice the Riemann zeta function evaluated at the value 3. Okay. So, there is a function called the Riemann zeta function, Riemann zeta function. So, twice this integral is 2 times the Riemann zeta function evaluated at a value 3, and this integral has a value which is 2.404. Okay. So, this has a fixed value number. The bottom line of all of this is that the number density of photons, we are interested in the number density of photons. The number density of photons scales as t cube, right. The energy density scales as t to the power 4, the number density of photons scales as t cube, and the relation that you get is that the number density of photons, you put in the numbers, right, at present 2.73. So, you put in the value, current value of the CMBR temperature, and what you get is that the number density of photons is 420 into 1 plus z cube photons per centimeter cube, right. So, 420 CMBR photons in 1 centimeter cube right over here. Every centimeter cube of space now contains 420 of the CMBR photons, and with the redshift the temperature scales as 1 plus z. So, the number of photons, number density of photons scales as 1 plus z cube. Okay. Another way of thinking of it is that the photons are conserved. So, the number density scales as 1 a to the power minus 3. Okay. So, that is the photon number density. Now, a quantity of interest is the entropy of each photon, entropy per photon. Okay, entropy of each photon is meaningless. Entropy is a thermodynamic quantity, but what we can calculate is the entropy per photon. Okay, so let us calculate the entropy of the CMBR, the entropy per unit volume. So let us take a volume, unit volume, okay, and heat it from 0 to T. So heat it adiabatically. Okay, I mean heat it without doing any work, not adiabatically. Heating it cannot, that's forget about it. Okay, that was a mistake. So consider a volume like this, unit volume, volume is held fixed, and we heat it from 0 to T. Okay, and we calculate the entropy that is generated of the radiation inside this. Now the entropy of something doesn't, if it's an equilibrium process, it doesn't, it depends only on the final state. Okay, so it doesn't matter how I reach there. Okay, so this is one way. This will, the result that I get if I calculate the entropy of the radiation inside is going to be the entropy of the CMBR per unit volume. Okay, so the entropy per unit volume of the CMBR is 0 to T. Now, to bring it to a temperature T, you have to give it some heat, and the heat is the internal energy inside because I do not do any work. So, it is going to be D A, the Stephen-Boltzmann constant, T to the power 4, that is the heat I have to supply, divided by T, right. We know it is dQ by T, the entropy. So, this is the entropy of the radiation inside this unit volume, okay, and this is equal to 4 AB, and I have this is T prime, this is T prime, okay. So, this is 0 to the temperature T. So, 4 I get when I differentiate this, the Stephen-Boltzmann constant is there. Now, the integral that I have 1 power less when I differentiate, 1 power less when I divide. So, I have T square T prime square dt prime. So, the entropy per unit volume is 4/3 T cube. So, the entropy scales as T cube, which is proportional to 1 plus Z cube, the entropy per unit volume, right. The number density of photons also scales as 1 plus Z cube. So, the ratio, you can calculate the ratio, okay, of the entropy per unit volume to the number density of photons S by n gamma, and this ratio is independent of Z redshift, and then this ratio comes out to be 3.6. Okay, so it is of order unity. The entropy per photon is of order unity. Okay, and you can actually make this ratio dimensionless by multiplying it with a factor of kb. Okay, by I have, okay, sorry, this ratio as it is written here is not dimensionless, but we can multiply it by a factor of kb. So, let us see which has to be, the denominator has to be multiplied by a factor of no, S by kb. Okay, this has the same dimension as, so I can divide by kb. Okay, this has the same dimension as the number density. So, the quantity that I have written here is actually this. Okay, the entropy divided by Boltzmann constant into and number density of photons. This is a dimensionless number. Okay, you can check for it yourself, straightforward, very simple to check. That entropy divided by Boltzmann constant is a dimensionless number. This has the same dimension as the number density of photons. Okay. This has the same dimension as the number density of photons. We are doing this for a unit volume. So, this has 1 by volume, this also has 1 by volume. The ratio of these two is dimensionless, and it has a value 3.6, which does not change with redshift. Okay. I forgot to tell you that the ratio of the specific heat capacity of the two, of the CMBR, of the baryons and the CMBR, that also does not change with redshift. Okay, that is something which is absolutely constant. This ratio that we just calculated over here does not change with redshift, because this heat capacity is T cube, this heat capacity is proportional to the number density, both of these scale as a to the power minus 3. Okay, so, this ratio also does not change, and it is invariant as you go back into the past. Similarly, the ratio of the entropy per photon, this ratio, this quantity does not change, it is of order unity, okay, for the CMBR. Now, another quantity of interest is the ratio of the number density of baryons to the number density of photons, right. I have already told you how to calculate the number density of baryons. You take the critical density multiplied by omega baryon and divided by the mass of each baryon, okay, the mass of one proton hydrogen atom, and number density of photon I have already told you how to calculate. Now, this number density of baryon scales as 1 a to the power minus 3 or 1 plus z cube. This also scales as 1 plus z cube or a to the power minus 3. So, this ratio is also unchanged with the expansion of the universe. Okay, neither photons are destroyed nor the baryons are destroyed, another way of thinking of it. So, if you calculate this, I have told you how to calculate this, and I have told you how to calculate this. So, when you calculate this ratio comes out to be 1.12 into 10 to the power minus 5 omega baryon h square. No, sorry, 10 to the power minus, okay, this is the number density of baryons, okay. This is just the number density of baryons, protons per cc, okay, that is the number density of baryons. And if you calculate the number density of baryons to the number density of photons, then this ratio comes out to be 2.7 into 10 to the power minus 8 omega baryon h square, okay. So what we see is that the universe, the number density of particles in the universe is dominated by the radiation. If you look at the sheer numbers, the number density of photons in the universe is much larger than the number density of baryons, much larger, okay, many orders of magnitude larger, and this is not changing, okay, this does not change with redshift. So, even if I go back into the past when the universe was much hotter, this much smaller, this thing does not change, okay. Another thing is that the entropy per baryon, so the entropy in the radiation, entropy per baryon, this is a very large number. The entropy in the universe is mainly in the radiation, the matter, the gas, whatever gas you have, any such baryons, they contain a very small fraction of the entropy. So, if you calculate the entropy in the radiation and per baryon, that number also turns out to be extremely small, because the number, that is a number of order unity. So, if you calculate entropy per baryon, that is that is a very large number. Entropy per baryon turns out to be a very large number, okay. The entropy of each photon is very large, so the entropy per baryon turns out to be the inverse of this. The entropy per baryon is roughly the inverse of this, okay. Entropy per photon is of the order unity, baryon per photon is this small number. So, entropy per baryon is a very large number which is of order unity, okay. So, the ratio of the entropy per baryon is an extremely large number, and this large number does not change, okay. So, entropy per baryon, this ratio number so the entropy density by the number density of baryon, this ratio is an extremely large number that you can see from here, and this number is a constant, okay. So, the entropy is mainly in this, is all in the radiation, and this number is a constant, as we have seen. It is a constant all the way to a temperature of around 10 to the power 10 Kelvin, okay. Because it is adiabatic expansion, and we have, right. So, we have also seen that it is an adiabatic expansion, and these things all scale in the same way. So, as 1 plus z cube. So, this entropy by baryon, this ratio remains a constant all the way to temperature of 10 to the power 10 Kelvin. At temperatures higher than, at what happens at this temperature is that you have the positron electron annihilation, okay. So, at temperatures, at this temperature you have positron electron annihilation. At temperatures higher than this, in addition to the cosmic microwave background radiation, you also have a bath of positron and electrons, okay. So, let us move. So, I have, what we have done till now is that I have given you some idea of various quantities which are for the calculated for the cosmic microwave background radiation. Okay. Now, let us have a look at the thermal history of the universe. The first point is that at temperatures T greater than 10 to the power 10 Kelvin, what do I mean by this? So, let me just get the picture which I had drawn. Can't find the picture. Okay, I can draw it for you again. It's a very simple picture. As I go back into the past, I am an observer over here. As I go back into the past, so further and further away, the temperature of the universe increases. Okay, so in the past, and then when I am sufficiently back in the past, the temperature will exceed 10 to the power, it scales as 1 plus Z, the temperature. Okay, temperature is proportional to 1 plus Z as I go further to higher and higher redshifts. Okay, so sufficiently back in the past, the temperature is now 3, around 3, it would have been more than 10 to the power 10. At this temperature, the cosmic microwave background radiation is sufficiently hot to excite neutrinos and antineutrinos. Okay. So, we assume that there are 3 flavors of 3 species of neutrinos and each of them has 2 polarizations. And in equilibrium, the neutrino and antineutrino can combine to give photons, and photon can spontaneously produce a neutrino antineutrino pair. Okay, so when the CMBR is sufficiently hot, more than 10 to the power 10 Kelvin, this reaction will they will be in equilibrium, okay, through this reaction. At lower temperatures, this will not occur. Okay, so you have to go to a temperature of more than 10 to the power 10, and these neutrinos will all be in equilibrium with the radiation. Okay. Now, if you have some particles in equilibrium, then this is the neutrino, this is the antineutrino. Okay, if you have particles in such equilibrium, chemical equilibrium, then the sum of the chemical potentials should be the same. Okay. So, the chemical potential of the CMBR of the photons, this is the photons, okay, CMBR photons will be equal to, in equilibrium, the sum of the chemical potentials of the neutrino and the antineutrino. This we know, okay, in equilibrium. From statistical mechanics, it is known that this will be true. Okay. Now, for the photons, we know that the chemical potential, thermal photons, we know that the chemical potential is 0. Okay, so the sum of these two must be equal to 0, right. So, what we know is that the sum of the two must be 0, or the chemical potential of the neutrino and the antineutrino must be opposite of one another. Now, the distribution function for the neutrinos, assuming that they are relativistic, is of this form. There is a factor of 2 because we have assumed 2 polarizations for the neutrinos. So, it will be e to the power exponential Pc by kT plus 1, oh kT, sorry, kT minus mu. So, let me just cut this to exponential Pc minus mu by kT plus 1. Okay, that is the difference from the CMBR, the photons, that these are fermions, so it is plus 1, and for these particles we can have a chemical potential. okay, and the chemical potential for the neutrinos and the antineutrinos should be opposite. Okay. Now, for okay, now if you assume, then what does this tell us? Okay, this tells us that if these two are different, see there is a possibility that the chemical there is a non-zero chemical potential for these two, and these two are different. Okay, so if these two are different, then there will be a difference in the number density of the neutrino and the antineutrino. If we assume that these chemical potentials are 0, right, that is the simplest possible assumption that you can make. So, if you assume this, then the number density of neutrinos and antineutrinos is exactly the same, because the number density is decided by the temperature as well as by the chemical potential. Okay. So, if you assume this, then the number density of the neutrino and antineutrino are same. If you assume that they are different, okay, so then you will have different number densities for these two particles. Okay, so we are going to assume this, that the chemical potentials are 0 or that they are non-degenerate. Okay, so we are going to assume that the chemical potentials of these particles are 0. If the chemical potentials are not 0, then you will have different number densities for the neutrinos and the antineutrinos. Okay. And right now there are very weak, it is not known, there is no reason, I mean a priori there is no knowledge about what these chemical potentials are. Okay. You can put some constraints possibly from different observations, but there is no, I mean there is no knowledge, we really do not have much knowledge about what these chemical potentials are. So, the most natural assumption would be to assume that there are as many neutrinos as there are antineutrinos and set both of them to 0, okay, which is what we are going to do. So, at a temperature of more than 10 to the power 10 Kelvin, there is this bath of neutrinos also, and we have to then calculate what is the energy density in this neutrino bath, what is the number density in this neutrino bath. Okay. Now, calculating the energy density and number density on the neutrino bath is exactly the same as calculating the energy density and number density in the photons, for the photons. Okay. The only difference is that the distribution function has a plus sign in one case, it has a minus sign in the other. Okay. So, this is something I shall take up briefly in the next class, and then we shall proceed forward.